So now that you've been exposed to a little bit about Java threads, we can start to focus on the other big topic in the course. Obviously, we'll come back and talk more about thread stuff later. And we'll start talking about Java synchronizers. So we'll talk about the different categories of capabilities that are provided by Java synchronizers. There's a whole pile of them. There are things called atomic operations, which are basically classes or lower-level mechanisms provided by the Java virtual machine and execution environment that ensure that an action either happens all together or not at all. So it's atomic. A good example would be, the transporter beam if you're a Star Trek fan. If you're a Harry Potter fan, it's like, disapparating when you go from one place to another, or using a port key or whatever. You don't want to end up with sort of part of yourself in one place and someplace somewhere else. So that's about atomicity. We'll talk more about that in a second. The next category of mechanisms that Java provides are called mutual exclusion mechanisms. These allow concurrent access and/or updates to shared mutable data without incurring race conditions. We'll talk a bit more about what race conditions are. Race conditions are the bane of concurrent programming because they cause things to happen in ways that corrupt the data, corrupt the state. We'll also talk about coordination mechanisms, and these are used to ensure that the computations run properly. And by that I mean they run in the right order, they run at the right time, they run under the right conditions, and so on and so forth. So it's kind of like a handoff. And then the fourth category of synchronization capabilities Java provides are called barrier synchronizers. And these are used to ensure that one or more threads have to stop at a certain point and can't go forward until other threads have also gotten to that point. So a good example would be the starting gate in a horse race or an auto race or a track and field race, right? Wouldn't be any good if people walked up to the starting gate and they just started running, right? You have to kind of wait till everybody's there and you go, 3, 2, 1, or ready, set, go, and so on. So those are the four major type of capabilities we'll be covering with Java synchronizers. And as you can see, they each do something a little bit different. So first of all, what is a synchronizer? Well, in Java, a synchronizer is typically an object, although we'll see there's a few cases where the really low-level stuff are implemented in a somewhat more primitive fashion, kind of like the difference in Java between, say, a stack and an int, right? An int is a bit more primitive than a stack. But a Java synchronizer is basically an object that is used to control the flow of cooperating threads based on the state of the synchronizer. So what are some examples of this? Well, if you've ever ridden on a train, you're probably familiar with the concept of semaphores or flags, which indicate there's already another train on this track, so stay off of that track. So it's a way of trying to make sure that multiple trains don't end up colliding on a shared track. And that's something that's called a semaphore. We'll talk more about semaphores later. But basically, it's a way to try to allow cooperating stuff, trains in this case, to share something, a track. Obviously, in the context of Java and threading, the things we're sharing are typically data or objects, and the things that are sharing that data and objects are typically threads. And I had a good question at office hours today about sort of what's a thread versus a function. So a thread, as we've talked about, I'll first give you the technical explanation. I'll give you an example from everyday life. A thread is basically a unit of computation that can perform work or perform functions, perform tasks, perform methods, can do stuff. Really what it's doing is it's running instructions that are written in the Java execution environment or the Java virtual machine or whatnot. So that's what a thread is in computational world. A not too bad way to think about what a thread is to think about a thread like a person, right? A person is someone who's capable of doing work. And you can imagine if you have, n people, 7 people sitting in a row, each person could do different work. Some people could be listening to the lecture, some people could be daydreaming, and so on, right? So each person could be doing something different. And if you move away from the environment of a classroom, obviously, you're talking on the phone, you're texting your friends, you're reading a book, you're studying, whatever you're doing. So that would be an example of a thread or threads, each doing some different pieces of work. And obviously, over time, in our daily lives, we do lots of things. Very few people these days just focus on one thing the entire day. So you're doing lots of different stuff. So that's kind of as if, each thread, each person was capable of doing different functions. Now, someone else asked a related question, which is how does parallelism and concurrency relate to each other? So you can think of concurrency as being logically simultaneous. In much the same way, if you have a single person, you can multitask, right? You could be talking on the phone, you could be looking stuff up on the web, you could be texting your friends, you could be chatting to somebody, right? You could sort of do all those things at the same time. Now, chances are you're probably actually not doing all those things at the same time. Physically, you're time slicing your attention between different things. And you're doing it pretty fast, right? Because you're a good multitasker. So that's kind of concurrency. You've got one unit of execution, you switching quickly between different things. In contrast, parallelism would be like having, n people all literally doing things physically at the same time. Like, let's say you're, digging a ditch or something like that, right? So each person has a shovel. Each person is taking their shovel full of dirt and throwing it someplace. So that would actually be physically doing things in parallel. So that means you're really doing things at the same time, whereas concurrency is more like logically doing things at the same time by slicing your attention. And of course, on a modern processor, you could have both of those things happening. You could have n cores, where let's say n is 4, and then you could have m threads, where m might be a very large number, like 12 or 100 or whatever. And at any given time, 4 of those threads are actually running in parallel at the same time on the cores. And the operating system and the virtual machine and execution environment and so on can be switching back and forth quickly between all the other threads so that over time, everybody gets a little chance to run on the cores that are available. So hopefully that gives you a bit more intuitive sense about these concepts. So given the concept of things running either concurrently or in parallel, synchronizers are there to coordinate so they don't smash into each other and cause problems. Java synchronizers are designed to ensure that threads interact in ways that will obey certain properties. So if you've got a bunch of threads, we want to make sure that they obey certain properties, mostly so they don't end up crashing into each other and causing more harm than good. Imagine a bunch of people trying to dig a ditch where they're just all like smashing their shovels together because they haven't coordinated who's going to be digging where. It gets to be a big mess pretty quickly. So here are some of the things that synchronizers can do. The most typical thing that you do with a synchronizer is ensure that you don't corrupt shared mutable data or shared mutable state. You don't want things crashing into the same location and causing an accident, right? Causing a corruption of that state. So let's take a look at an example. Here's an example. I should actually call this, non-atomic ops. What we think we're trying to do here is we think we're going to write a little class that has a field called mCounter, and we want to have an increment and decrement method, 2 of them. And in one thread, we're going to be calling increment, and the other thread we're going to be calling decrement. And we would like the behavior, the output of this thing to be predictable. We don't want the value of counter to be corrupted. But unfortunately, because there is no synchronization in this example, there's no synchronized method or no, use of a synchronizer, the behavior of running these things concurrently in multiple threads is undefined and unpredictable. Nobody knows what the heck this result will be, and it will be completely erroneous unless you're incredibly lucky. And most of the time, it's just going to be bizarre results. And that's because there's nothing synchronizing the increment and decrement of this counter. There are lots and lots and lots of ways to solve this. Here is a very simple way of doing it, not the only way, not even necessarily the best way. The simple way to do this is just to make increment and decrement synchronized methods, which means only one of them at a time can be running, and therefore only one of them at a time can increment and decrement the mCounter field, even if they're running in different threads. So that's one common capability of a Java synchronizer. There's lots of other stuff that they do, but that's one of the common things that they do. And of course, we're going to talk a lot more about this, and we'll talk about what synchronized does, and we'll talk about other aspects of this like visibility and so on. Another thing that synchronizers do is they ensure that interactions between threads occur in the right order, at the right time, and under the right conditions. So this is more about sort of coordination, passing things off. So here's a very simple example. Let's say we want to write a little program that that plays ping pong. If you probably won't remember this, but if you get like an old school gaming arcade, one of the very, very first computer games was something called Pong. And it would basically involve, it was really very primitive. You could have it on your TV screen. And I remember this when I was a kid because it would just come out. It was so cool. And you would basically hit the ball back and forth, and there'd be sort of two paddles, and they would hit the ball back and forth like playing ping pong. And obviously, if you want to play ping pong, you need to alternate, right? It doesn't do any good for one player to keep hitting the ball like a million times and nobody returns it. That doesn't even make sense, right? So if you want to have a ping thread and a pong thread that take turns, if you don't use the right synchronizer, you can end up in a situation like this, where you'll say, ping, 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 and then pong, 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 which is not at all like playing ping pong. It's some bizarre variety that has no meaning in reality. So what instead you want to do is you want to have a synchronizer that ensures that these threads take turns doing ping, pong, ping, pong, ping, pong, and so on. And they do it in the right order and under the right conditions. The right conditions being, it's my turn, right? So that's kind of the right order. So we'll see that there's a bunch of synchronizers in Java that make it possible for you to control the coordination between these different things. So the way to think about this is the first set of things is kind of about mutual exclusion, and then the second thing here is kind of about coordination. Okay, so that's a very high-level view. We will obviously come down and talk about all the mechanisms later. Just to give you a little foreshadowing about why you should care about this, assignment 1B, which I will put out shortly, will have you be doing a little synchronization stuff. So that's why we're covering this. By the way, just so you understand the process, you'll submit assignment 1A by tonight. It doesn't have to be perfect, but you have to make a good faith effort to make it work. Submitting something that is incomprehensibly gobbledygook is not a good way to do things, and you get penalized for that. What I'll do is I will take a look at your submissions. I will then give you feedback on your submissions, and then you'll have a few days, well, actually, you'll have a little while to fix it, because all you have to do is make sure that your solution for assignment 2, or assignment 1B, includes fixes to my comments for assignment 1A. So then assignment 1B will come out. I'll probably put it out like tomorrow or soon, and then you'll take a shot at that. You'll address my comments on assignment 1A, fix those things. You will implement assignment 1B. Then there'll be a submission in a week or so whenever we do that for assignment 1B, which also includes the assignment 1A fixes, if any. I will then review that. Then I'll give you feedback on that. And then finally, you'll get a chance to address my comments on assignment 1B, and then you'll submit your final version. And that's the version we'll grade. So the point of all this is to give you lots of opportunities to get feedback, lots of opportunities to get it right. So in general, most people do pretty well on the assignments. They're not meant to be mind-numbingly hard. Some of them are harder than others, but the point is that you get plenty of feedback. Just don't fall behind. That's the thing that I ask of you, because if you fall behind, then it gets really tough. Okay, so Java synchronizers. Java synchronizers address various types of complexities. One of the key types of complexities they address is something called inherent complexities. There's also something called accidental complexities, which we'll perhaps talk about briefly, but the key point is inherent complexities. And inherent complexities are things that are just hard about doing certain aspects of software. It's the rocket science, right? Accidental complexities are just, because historically people have used low-level languages like C, where it was really easy to shoot yourself in the foot. And so those are things that are sort of self-imposed limitations by the choices we make of the tools that we use or the languages we use. Inherent complexities are the kind of things where it's like, even if you use a good language like Java that takes away a lot of the sharp edges and dark corners of C, it's still hard. So here are some of the things that are hard about synchronization that Java synchronizers help you with. And one of them is atomic ordering, which, as we talked about before, is just a way to ensure that an action either happens all at once or doesn't happen at all. So again, the transporter beam is an example of that. Here are some simple examples of the issue of atomic ordering. So what we'd like to be able to do is assure that operations on a field accessed by two threads. So this is going to be a shared mutable data, right? A field that's shared mutable data or shared mutable state. Let's say we have two threads, thread 1 and thread 2. We want to make sure that if we do an operation on a field, that it is atomic and not sort of munged together in some strange half-baked way that's a little bit of this and a little bit of that. Again, think like splinching if you're a Harry Potter fan. So here's an example. We've got thread 1 and thread 2. We've got a field that's a long, and thread 1 is going to initialize the field to 0. Then it'll go ahead and read the value of the field, increase the value by 1, and write the value back. And likewise, we want to have thread 2 read the value of the field, increase the field by 1, and write it back. So if all goes well, then we should end up with the value 2 if synchronization does its job. However, if we don't use synchronizers properly, then these 3 intermediate operations needed to increment a value of field by 1 could be interleaved, and you'd end up with inconsistent results. And we'll see some examples of that in a second. So the basic point is that atomic ordering makes sure that things happen all at once. When you increment something, you read it, you increment it, you write it back. That's atomic, even though there may be multiple steps involved. If you're trying to do these kinds of things, if you're trying to increment a field by 1, let's say you have an int or a double or a float or a char or a long, these all the ones that are lowercase int instead of integer, which is uppercase. Those operations will be corrupted if multiple threads do them at the same time. So unless you use synchronizers, of course. Atomic ordering is supported by the Java Atomic package. We'll talk a lot more about that later. There's a package called Atomic, and it's got a bunch of interesting things in it. You'll get a chance to play around with some of these in the next assignment. I think you end up using Atomic Boolean, which is kind of a cool class that very efficiently checks if something is true and checks if something is false. And you can update the Atomic Boolean from true to false in an atomic way, which is kind of the point. The next concept, mutual exclusion, we've kind of talked about this before. This prevents simultaneous access to shared resources within a critical section. Often, not always, but often the resources involve mutable shared state. So once again, we're trying to protect things. And as we'll see, mutual exclusion is a bit more generalized than atomic ordering. Atomic ordering really means just sort of incrementing or decrementing the values of fields atomically. But mutual exclusion can be a larger number of things happening within this so-called critical section. The example I've used before is the restroom in an airplane, which is obviously used it's used for more than just incrementing a value, right? You use the restroom for other things than just incrementing and decrementing values. So, but the mutual exclusion stuff still applies. The rule is that when the thing is locked, it says occupied, or it says vacant. No, it says occupied when it's locked. And the rule is you queue or sit in your seat if you're trying to get to the front of the airplane. And you can't actually go in until it says vacant and the person in there leaves. That's the mutual exclusion property. If you do not obey mutual exclusion, then you can end up with these race conditions. Again, race conditions are these tragic things that occur that corrupt the state of your program because your program depends on the order in which things run. And if they don't run in the right order, if you get unlucky, which is what usually happens in concurrent and parallel programs, you'll get the wrong results. So I like to think about race conditions as kind of, I always use this picture of an accident, right? Two entities, 2 threads, 2 vehicles tried to occupy the same space at the same time, and it corrupted one or both of them, right, by smashing them up. You can read more about race conditions here. Race conditions are something that occurs for hardware, for software, for all kinds of things. Obviously, we're primarily concerned with the software manifestation of race conditions, but take it on faith that the hardware level will also be doing things to cause problems if you don't use the right software primitives to make it work properly. Here are a couple examples to illustrate this. So let's imagine thread 1 and thread 2 are doing stuff. So if we don't have synchronization, then if we increment this thing by 1 and then simultaneously write back the incremented value while this thread reads the value, right? So it starts out with 0, this thread increments it, and then at exactly the same moment, because we've got multiple cores, right? We've got multiple core machines, so it really could physically happen at exactly the same time. Thread 1 writes the value back to the field while thread 2 reads the field. What's the value that thread 2 gets? Is it 0? Is it 1? We don't know, right? Because there's a race condition, because there's no synchronization involved. And these are called basically read-write conflict. So read-write conflict would occur in the absence of synchronization if you try to apply two operations to the same field in parallel, and it turns out that they would conflict with each other. So this is an example of a read-write conflict. There's another example, which is more or less the same thing, just a different variant. It's a write-write conflict. So here what we've got is thread 1 comes along, initializes the field to 0, reads the field, gets 0. Thread 2 reads the field, let's say it gets 0. Thread 1 increments by 2. Thread 2 increments by 1. And then they both try to write the value back at exactly the same time. And the question that arises is the value 1 or is the value 2 when we're done? That's a write-write conflict. We're writing the results back. And in the absence of synchronization, we don't know which of those things will hold, will apply. And it gets ridiculously complicated when you start dealing with caching at the hardware level with multi-core caches and so on and so forth. The bottom line is, if you don't use synchronizers properly, you can end up with read-write conflicts and write-write conflicts, both of which are bad, both of which will lead to chaos and insanity in your solutions. This is particularly problematic on multi-core processors. It's always been an issue that's been out there, but with multi-core processors, it's an issue that pretty much everybody faces now because pretty much everybody's using multi-core processors. In fact, it's almost impossible to buy a single-core processor these days. You really have to work at it because everybody's trying to maximize the silicon yield, and so they want to have multi-core, if for no other reason that Moore's law has kind of petered out with respect to processor speed, though not processor density or transistor density. So we have lots and lots of transistors. They just aren't getting a whole lot faster to do the processing. But you can have lots and lots of cores for basically the same price, or cheaper, as it typically works out. And so what we end up with are these multi-core platforms that end up having caches. Each core, and then each thread running on each core, will have its own cache. And so if you do operations, like if one thread writes a value that's a non-volatile, that's what NV stands for, non-volatile, if it writes to that, then in the absence of synchronization, it's not clear when that value will be propagated from cache 1 up to main memory, such that if someone else is to come along and read the value of that field, it'll get a different value. So this guy could write 7, this guy could write 42. This guy does a read. What value does he get? Does he get 42? Does she get 7? Does she get something else? Who the heck knows, right? The point is that without synchronization in your code, you don't know, because the underlying hardware will let things run out of order. It tries to optimize stuff. It tries to avoid pushing memory through the memory hierarchy unless absolutely necessary. So you end up with very strange results. So mutual exclusion mechanisms in Java are designed to remove the ambiguity and the non-predictability, thereby ensuring your programs have a meaningful result. And you can read more about memory ordering here if you're interested. This is the way the world is going for lots of different reasons. Mutual exclusion in Java is supported by the Java locks package, which includes reentrant lock, reentrant read-write lock, stamped lock, and so on and so forth. And I should also point out that mutual exclusion is also supported by the Java built-in synchronized keyword. So there's a built-in keyword called synchronize. You can either apply to a method or to statements within a method or within methods. Those will also ensure mutual exclusion. And we'll talk a lot more about that stuff later. All right, so that's mutual exclusion. The next topic is coordination. And this is used to ensure that computations run properly, either in the right order, as we saw with our ping pong example. So the ping pong example, make sure we do ping pong, and so on, at the right time. So we might want to make sure that the timing is obeyed, so that something has to occur before something else, or something has to occur at a particular time. And the final piece is under the right conditions. And that's what you're doing with your Palantiri stuff that we're talking about. So the Palantiri simulator assignments that you'll be doing throughout the class will be applying different types of synchronizers in order to ensure that the different beings are gazing at the right number of palantiri under the right conditions, namely when there's one available, right? So if there's not one available, you've got to wait. When there is one available, you get it, and then you can gaze and look at it. Coordination is supported in Java by a bunch of different ways. The concurrent and locks packages, there's things like condition object and semaphore, which we'll be talking about at length and you'll get a chance to program with. And then there's also these Java built-in monitor objects. And there's something called a wait queue, and there's wait and notify all. These are used in order to be able to cooperatively coordinate between multiple threads, trying to do some broader thing, like insert something into a queue or remove something from a queue and so on and so forth. And then the fourth and final category or inherent complexity are barriers, which, as I mentioned before, is just ensuring everybody starts or stops at the same time to make it fair. And we'll talk later about different types of barriers. There's entry barriers, something like the starting gate at a horse race or an auto race or a 100-meter dash. Those are entry barriers. You start everybody at the same time. And there's also some stuff we'll talk about called exit barriers, where you all have to coordinate to leave at the same time, right? So there's certain things that work in both ways. An exit barrier might be something like letting kids out of elementary school to go to the carpool. You know, you kind of line them all up, and then the bell rings, and then they can all go forward at the same time. You don't want them just sort of wandering out piecemeal and getting run over. Barrier synchronization is supported by the Java concurrent package, and we'll talk about the main classes that do this, which are countdown latch, cyclic barrier, and phaser. You'll definitely get a chance to program with countdown latch and cyclic barrier. You may get a chance to program with phaser. We'll see. So let's talk a bit about how common synchronizers are. And this is really interesting. So it turns out that there are lots and lots and lots of different synchronizers provided in a Java platform or on the Android platform. So the Java language contains some features that synchronize threads. So things like volatile variables, we'll talk about those. That's a form of atomicity that's built into Java. They have built-in monitor objects, which handle things like mutual exclusion and coordination. So those are kind of baked into Java, the language, Java TM. There's also synchronizers, and that's kind of at the execution environment level, the JVM, the Android runtime, and so on. That's that level. That's kind of the lower level part. And so, not surprisingly, these are very efficient, but they're very limited in what they can do. At the threading and synchronization packages, a package is just a grouping of Java classes. There's a bunch of synchronizers provided there, so Java atomics, locks, semaphores, condition objects, reentrant locks, stamp locks, blah, 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 blah. There's tons of things there. And that's all part of the Java class library, which you can see here shows the fullness of what's there. We're just talking about a piece of it, of course. And in this particular class, we're going to spend more time focusing on synchronization than we actually will on threading. And there's a reason for that. In the other class, the class I'll teach next fall, ironically enough, we flip it around. We talk just about nothing about synchronization in the next class, and everything's about parallel processing. And the reason for that is that, as we talked about before, with parallel processing, you typically try to avoid sharing anything. And so the need for synchronization just disappears because you're not sharing anything. Whereas with concurrency, which is the focus of this class, you're spending a lot more time on sharing of stuff, so synchronization becomes a lot more important. The complexity of synchronization arises from trying to coordinate the interaction of different types of entities, mostly threads, that can run concurrently. And this is one of my favorite pictures to demonstrate the need for synchronization. Does anybody know what this is? This is probably like Bangalore at rush hour. Actually, having been at Bangalore, it's pretty much Bangalore at any time of the day. So you can see there's just a million different vehicles, different threads of different shapes and sizes. There's There's trucks or lorries, there are cars, there are basically what look like little pedal vehicles, there's motorbikes, there's bicycles, there's pedestrians, all just randomly running around. It's completely insane. When I went to India a few years ago, I'll never forget, in India, if you have a 2-lane highway, 1 lane in each direction, if nobody is driving towards you in the other lane, people will just switch over and they'll have 2 lanes going in one direction. And then at the very last second, they swerve back if a car or a truck is coming toward them, which is a little bit unnerving if you have if you've never driven in that environment before. It's also funny too because the rules of right-of-way, in the US and in the UK, there's rules of right-of-way, like if you're at a 4-way stop, the vehicle in the right takes precedence. In India, it's whoever is driving the bigger vehicle, they have the right-of-way. So if you've got like a little bicycle, you've got to get out of everybody's way. If you're driving a big truck, you have the right-of-way. And it's just absolutely crazy. Fascinating place. I love it. But it was very different from driving around here. In fact, a lot of my grad students, when they've gotten done with their programs here, a lot of people come from India, obviously, for grad school, they have a hard time going back home, and they hire chauffeurs because nobody wants to drive anymore, right? It's just so chaotic. It's pretty funny. As we talked about before, the parallel frameworks in Java, the parallel streams, completable futures, they address a lot of these issues by this divide and conquer mechanism. And isn't that a great, GIF showing divide and conquer, right? You're breaking stuff up into pieces. So, like I said, we won't talk a whole lot about that in this class, but if you come back next fall, we'll cover it. So that's the end of the overview of Java synchronizers. Obviously, there's a lot more to it than that, but that was just giving you the high-level view.